a couple things there. So I want to go over our agenda for today really quick, just sort of what we're going to be covering. The very first thing we want to do is what I'll just characterize as the elephant in the room. So we're going to talk about the current state of testing and a little bit about laser cut parts. We're going to share with you what we know, and we're not going to guess for sure what we know. We're also going to do product updates, and those two presentations will primarily be done by Ryan Johnson, who's standing behind me here. He's the president of the company and our chief engineer. So that after the product updates, we have two engineers from our engineering team. Brian Dickman here is one of those engineers, Max Alvarez, black hat on, is our test pilot and also an engineer on the team. So just to get started, as many of you know, we started making parts using a fiber laser cutting process in about February of 2022, so about a year and a half ago. And that process continued until about the end of June of this year, 2023. And Brian's going to talk about that, but what I want to make sure everybody's aware of that, why we're talking about this, in case you're not aware here in the forum. So we received reports over the last little while from customers. They kind of trickled in, and they came in some larger numbers of small cracks forming in the edges of dimpled holes. And so we are conducting an investigation that the team will go into during the presentation. I'm going to ask you to hold questions till the end, number one. And secondly, if you have a question that's specific to just your project, if we could do that after the presentation, we're more than happy to hang around and do that. That would be really good. We can't necessarily answer every really specific, detailed individual question. There are some questions that we don't have answers to yet, and we're working on those. We're working really hard. It's one thing I do want to say is that we have a significant team back in Vans, led by these guys and quite a few others who are dedicated to doing the research on this that Ryan will go into. So they're working hard. It's literally a 24/7 process. So with that, I'm going to hand it over to Ryan Johnson, President and Chief Engineer of AirVenture.
Thanks everyone, and thank you, Greg. I think it's a great set up here. He's going to report where we're going. So what's happening? Of course, the laser cut holes. We already discussed that. The first thing to cover is that these parts are now being punched. We didn't really have the availability during COVID to punch parts in the Portland area, but we've acquired some new partner fabricators that are helping us pick up the slack. How do you know you have a punched part? It has blue vinyl on it. Laser can't cut through blue vinyl. That's one way to know that there are some heat-treated parts that do not have vinyl on them. So when you look at parts, just because it doesn't have the blue vinyl does not mean that it isn't punched necessarily. But know that the parts that are coming from Vans now, we have moved back fully to the punched process. There are some parts that were historically laser cut at Vans, or parts that are cover plates, etc., that are very low stress and have very low likelihood that are still trickling out as laser cut, but even those will be phased out. So it's back to the full punch process. So any part that would carry stress through it, significant stress, we're moving back to the punch process. So I just want to go through a few definitions here before we start into the presentation. There are fatigue cracks. So that would be a crack that starts from a stress level that is repeated. It could be a low stress level, a high stress level. There's solidification cracking. We're going to go into that. The solidification cracking, what happens there is if you heat up the material as it cools, the precipitates within the material, there's additives to 2024 T3 that give it strength. And those other things besides aluminum, they coalesce on a boundary. And that boundary becomes more brittle, especially if that becomes a wide boundary during solidification or as it's cooling down. That presents a problem. Overload cracking, that's a term that I'm just going to coin for this presentation so that we differentiate between a fatigue crack and an overload crack. An overload crack, what we're defining that is a crack that's happening during the dimpling process. So you can see in that upper picture, laser pointer here, there's a crack that's opened up right there during the dimpling process. So that was what has been more recently reported at VANS and caused us to go back and take a look at what was going on in the process. The fatigue critical feature, a part may have many features. For example, the notch, relief notch where flanges are bent. It may have other features in it that raise the stress level around that particular feature. So the fatigue critical feature, many things could be features that eventually cause fatigue. That are normally in parts as well. Aluminum will eventually fatigue as you go long enough. The point is to design it in such a way that that doesn't happen within the useful life of the airplane. Stress concentration. So a point in the part where the stress is significantly higher than the surrounding area. Again, around a notch in the rib would be a good example of that, and I'll show a picture of that later. Limit load. Those are the loads. For example, your RV that's aerobatic is going to be +6 -3, so the limit load is +6 -3, what you expect in normal use, and the ultimate load is 1.5 times that. So just to clear those terms before we start in here. The root cause of the problem, the ways that the holes are specified to be cut, if you start in the center of the hole here and pierce the hole there, come around with the laser all the way around and in there, there's only a very small heat affected zone along the edge. And the advantage of a fiber laser, and why we looked into a fiber laser, is that it passes very quickly through the part and has a lot more power than the old CO2 lasers, where historically parts were not laser cut in the industry. And leaves a very small heat affected zone. Over here on the right, you have the start button in the center, it moves down, and the laser, what was actually happening from our laser cut vendor is they started in the center, they came down to the bottom. The laser has to pause for a very short time as it changes direction, goes around the part, and then stops in the same location. Another thing we discovered is every PO that we were sending over to these laser manufacturers, they were reprogramming every time. So what we thought we had settled out at the beginning of the process was changing over time. As a result, this little red line at the bottom, we can see that there's a heat affected zone. And I've drawn this not necessarily in proportion, but what that does is it heats the edge of the part in a localized area, and then that cools down. And as it cools down, the precipitates gather along a boundary. That does create a zone that could be brittle, and when you dimple a hole, that can cause a crack there to form along that brittle boundary. So what was lasered? We did not laser skins. We accidentally lasered one flat bottom skin, and that was for a short period of time. Besides that, there was no skins laser cut. We have a list online of what parts were laser cut, and you can go online. That list is going to be changing actively over time as we identify which parts we have concern with that we want you to replace. For the most part, what was laser cut was understructure such as ribs, which are at much lower stress level. There were also laser cut empennage spars, the vertical stab spars, the elevator spars, aileron and flap spars were also laser cut at the very beginning. The thin materials were the only parts that were laser cut. So 040 and under, and then eventually just 032 and under. So getting into the testing that we're doing now, of course we have to do accelerated testing. There's no time to test full structures repeatedly. So how do we accelerate that process? And this is the methods that are used in the industry. You start out with coupons on the bottom. That's something that we can run through a fatigue test machine. I'll show you that in the subsequent slide. You move up to element testing or small assemblies, subcomponents, and then there is some full component testing that's required. here's some examples of that here at Vans. There's a coupon on the left, and then in the center, you see a D-cell loaded up that's about 250 pounds per rib. That's indicative of a limit pull-up load on that D-cell, and we're testing what happens to those ribs with different types of failures. We also tested it beyond ultimate, and we'll show that in a bit. And then on the right is component assembly testing, and I'll get back to that here in a minute. That's the RV12 stabulator, and we're testing that to limit numerous times. Here's the machine that we use. This is a calibrated and certified machine. It's the MTS test machine. We can do full test, tension to failure, as well as tension and compression cyclic testing. We can even set up a specific cycle if we wish to do so, program it into the machine. Here's an example of the different types of coupons we've done over the years. And just to be clear here, the coupon on the left here was from our testing in the late 90s. This starts out in 99 when we were trying to go to final sized holes. So we've been testing this way and at local universities for some time. Those coupons there were for final sized holes. The next coupon over is what we call a dog bone coupon, and that is not to test load through a rivet, but rather to test the edges of the parts. We want to be sure that the edges of the parts would not be affected by the laser cutting process. The one next to it has blind rivets in it, and we just want to make it clear that in the initial testing and subsequent testing, we have tested all different fastener types that you would see in laser cut holes. That testing, that coupon there laps the material over top of one another. So it's a single lap, and that's somewhat indicative of what happens in the airplane, and I'll show a graphic of that later. There's different types of loadings. There's somewhat peel load, where the skin is peeling up against the rivet, and in that case you would most likely fail the edge of the dimple, or even sometimes the dimple die mark fails before the hole itself. And then there's case where you have a skin against a solid member, and more of the load goes into shear. So instead of peeling the parts apart, the load goes directly into the rivet against the edge of the hole. And that's what you see on the right side of those specimens there. We have thicker material in the center of these specimens that make sure that the load is going into shear inside the rivet. Just an example of some of the coupons we've tested. And here's our recent coupon testing results. And I want to qualify this because we are not through with testing yet. And although things are looking hopeful so far, it doesn't mean we're going to find an area in which the life is reduced. But what we've seen so far, what you see here is the probability that a crack would occur or a failure. This is to full fatigue failure, so I should qualify that. We're testing these coupons until they completely break in both the punched configuration and then taking the same configuration and repeating it in a laser cut configuration. We're also testing laser against laser. There was some understructure where that happened, or skin to laser, in which case the skins were never laser cut and the understructure was. So what we can see here is that in some cases the laser is lasting longer than the punch. It has a greater life. And that's what we noticed from the beginning, and it is still the case that we're finding now. And I'll get into the further testing that we're conducting. With this round of testing, of course, we just don't want to trust our own machine, our own setup. Again, we've changed our own test methods as well to try to assure ourselves. We just don't want to repeat the same test we did at the beginning of this program. We've also went to a third party. This third party is a respected analysis company in material science, and they do everything from small mechanical projects like we're working on. They recently worked on the Oakland Bay Bridge, and they worked on other projects to that scale, material failures. So they're well known throughout the country, reputable, and what you're seeing here is that all the test data from Vans and that company is laying fairly closely on top of each other. And to give you an idea, the life of an airplane is somewhere down here. So we're well beyond the life of an airplane. The test data is correlating with a third party, independent third party, doing the same test as us, but I'll note here, go back to our machine. We have grips, clamped grips, and they have tried different methods of constraining the test specimen, as you can see there. So it's not exactly the same test, but we're getting the same results. So defining more about a dimple, this is a little bit hard to see in definition, probably in the back. This is a dimple that we've cut apart so that you can see what the dimple looks like inside. You can see that the rivet doesn't fully fill this void. Here is the top sheet, as you can see in blue there. We have the dimple rim. I'm calling it the rim. Defining terms here as we discuss this. This is the cone of the dimple, and this is the whole edge. So the highest stress, and I'll show a finite element analysis model of this in a subsequent slide. In finite element analysis, I'll get into that in a bit. It's observing the part inside the computer, dividing it up into little segments, and you can see how the stress flows through. So it mathematically calculates the stress in different areas of the part. But what we're seeing is that often the highest stress point in this rivet is up here on the rim of the dimple, and the failure will go through the rim of the dimple. And this is what we've seen from the early days, even back to 1999 was when we first conducted testing, trying to get to the point where we could punch holes at final size. Here's the finite element analysis model of the hole. And you can see from the top here the stress, I'm going to call this the 12 and 6 o'clock positions. The stress is being applied at the 12 and 6 o'clock positions here. You can see at the 3 and the 9 o'clock positions, there's a stress riser on the inside of the whole edge. We've taken the features, let's call them, or the cracks that are from the overload cracking, and orient them at the 3 and the 9 position. We're currently orienting, as you can see here on the right side, we also have a high stress area in the rim of the dimple, which is where the crack is going to. So we're taking the features we've tested here at the 3 and the 9 position, and we're currently gathering test data at a 45 degree and here at the 12 o'clock, 6 o'clock positions as well. So far, that testing is showing equivalent light to the other test, 3 and the 9 position, which is the graphs we saw earlier. Here's pictures of actual cracks. You can see here is the overload feature, and here is the crack itself that's going to the edge of the hole. And we need, we're constantly asking ourselves, why is this the case? That's also why we went to a third party, and we may also pull in others as well. One thing that we have done is look at the overload feature under a scanning electron microscope, SEM. And it's apparent that that crack at the end of the crack, when it's opened up, that we flex that crack open and then it closes up. And what that leaves is a stretched, formed portion at the end of the crack that has compressive residual stresses at it. And a case that happened in the real world that we're all familiar with is the Comet. The Havilland Comet. And they pressurized that airplane to 2.5 atmospheres, then relieved it. And when they did that, they introduced cracks into the structure that then opened up and closed up and left that residual stress crack. And then they ended up testing at 1 atmosphere for 16,000 cycles of flights, equivalent flights. And what the problem was the cracks that formed, that eventually fatigued their test specimen, formed other areas than where those initial cracks were formed. And as a result, they thought that they had a structure that lasted a lot longer than it did. But the reason was they had those compressive residual stresses at the end of the crack, and they weren't overcoming them with the 1 pressure cycle. In our case, these tears, we believe, do have this compressive residual stress. And so it takes quite a high stress to overcome that residual stress into the crack. And that's why that crack isn't propagating. But we don't know that for sure yet. And so we're continuing to orient that crack in different orientations relative to stress going through the part to see if we can drive that crack into a failure mode or continuation mode. But so far in our testing, we'll watch the cracks right before or as they start to form. They'll form on the other side of the nipple and go up to the whole edge. Or as you can see here, many times they don't even know that the crack is there, the overload crack. The other item that we've done, you can see here in this part, the grain direction is flowing this direction through the part. We've also oriented the grain direction in different directions to line that up with the feature, see if that makes a difference. And so far that hasn't made a difference either. This is a picture of loads on a rib. So this is a D-cell rib. And sorry, Brian, you're just coming around here. But the way a rib is loaded is you have a lot of air load distributed over here, and in 23,000 series airflow, when you do this pull-up or even a diving pull-up, that load is very much front-loaded. So as you saw that D-cell test with all the lead on the front of it, the load is concentrated over the front of that airfoil. That load, then this acts like a beam, and the rivets are more highly loaded as you go aft. These aft two rivets here, the top and bottom, are the most highly loaded rivets in that structure. So what we're doing is going through the airplane and finite element analysis and looking at the loads in the rib, rivet by rivet. And the good thing here is that those rivets alone carry most of the load and quickly drops off. So if anything were to happen, those rivets would start smoking, or you'd have some warning that something was going to happen. So far, though, we're looking at the loads at those locations, and they're quite low relative to the stresses that we've been running in, and I'll get into that in a second. So this picture looks grotesque. That's because we've taken the deformations in the structure and multiplied them by 10 or more. So know that this isn't how the structure would actually look under a limit load, but we're trying to show accelerated deformation there, just so that you can see how it is distorted. What we're showing here is the highest loads in this part are at the notches. This is the relief notches, which have been historically in advanced parts and in other similar designs for years. And we know that those aren't cracking. So if stress drives a crack and the stress at the holes is a lot lower than we're seeing at the notches, it's very unlikely that the holes will, that feature, if present, will continue to propagate. And I should say and clarify here, we're not saying that we want you to accept a feature in your part, but our concern here legitimately is that someone would have missed a feature during the build process and that would be present in the part. And so we're trying to do our due diligence to say, well, if that feature was here or in it this way, and go through the structure step by step to determine the ramifications of it. So what we're showing here is our thought process as we go through looking at the structure and what the ramifications be. This is a new test coupon that we're just starting into. The load is applied in this direction, and this has an angle on the sides of it. So the sides of the test is angled in, and it does two things. Depending on the angle, if you had the test oriented this direction, it would be in pure tension, and this direction would be pure shear. So we can go into the finite element analysis model and know the amount of the ratio of shear to tension and set the correct angle. For the worst case, we take the worst case shear rivet and the worst case tension. We apply both in this test. We'll also add notches in this, but what we're really curious about is the fact that as you apply an air load in between ribs, so the skin is being pulled up, there's actually a peeling load and it opens up and closes the flange of the rib repeatedly. So we want to know if the notch is going to fail first, the rib flange is going to fail first, or a hole with a feature in it, or holes with features in them, will fail first. So that test is starting this week. We're just finishing up the coupon test and moving on to these other tests. So this, for those that are curious, car 4B 270B, that was written as a result of the Comet investigation. And you can see here what it asks you to do is load the structure and fail a member of that structure. And as a result of that failure, you can't have a catastrophic failure, the airplane has to come home, and you can't have an aerodynamic failure either. So those are the things that we're looking at here. And again, what we're trying to look at is the redundancy of the structure. And showing that the structure has quite a bit of resiliency to it. Again, in this picture here, we're actually showing the crack forming from the notch itself, since it's highly likely that that would be the case. If the crack had formed at the rivet, it would have just chopped off the back of the rib, and there wouldn't be that much structural loss. So we failed that, and we're failing, we cut across top and bottom, and then also in the front lightning hole, but that's not shown here, and then load up the part. We're doing this with a full wing currently. The picture on the right is taking that structure. This is without any cuts in it, but this is just overloading it and showing you what that structure looks like. Again, we're only required under FAR 23 to go to 1.5 times the limit. This is at 2.3, and you see the buckling failures there in the rib. That structure is still holding its aerodynamic shape at that point. This is the RV-12 stabulator test, and I'll get into this in a second here, but 1 hour in flight school is equivalent to taking the structure to 1 limit load. So all loads that occur during an hour equate, and there's an AC for this that I'll get into, to 1 limit load cycle. And we tested this to around 32,000 cycles when we finally turned off the machine. This had worst case rivets, laser cut holes in it. And why we tested the stabulator is in this structure, you have laser cut structure that's riveted to laser cut structures. So you have the worst case scenario. And it's also a highly, as far as stress levels go, the amount of load at an individual rivet is one of the more highly loaded structures in an RV-12. So we went to over 32,000 cycles without any apparent effect on the structure. And we'll do further testing on that failing members inside of it as well. So where does all that come from? The equivalency that I was just talking about, 1 hour in flight school is equivalent to 1 hour of 1 minute load cycle. This is AC 2313A, which talks about fatigue testing and failures in aircraft. And here these are lines that just are representative of the aluminum that we use in the airplane. This is a logarithmic scale. Okay, so these numbers are gaining here by the log, and you're going from 10,000 to 100,000 to a million to 10 million. So if you had this on a linear scale, it would actually be a curve that looks like that. And you use this graph, you have the alternating stress off your mean stress, you find that, and it tells you the number of cycles that the material will be expected to endure. And then these are charts where you can correlate in a flight school that a certain numbers of loadings at certain cycles would be equivalent to. And you find that on the last graph. And I won't go into this in detail in this presentation, but you can come back to us and explain it further at the booth. This is called Miner's rule, which is what is used in the type of airplane applications we have. And in effect, this is telling you that if you load a coupon, where we're loading these coupons, we take them, and I'll show this in the next slide, to limit load, or as much as they can take. We'll back it off just slightly, and we find the stress level of the life at that point. But these rivets are at a much lower loading. So Miner's rule is the way that you can take the amount of life that you measured at this high stress level and translate it into, okay, I have a finite element analysis model, I have rivet locations, and how long will the life be at all those locations? Again, we already covered this. So you take a coupon, and if you load it fully in tension and then go to half reversal, those are the coupons that have the bend edges on the side, so we can actually apply compression with a half reversing cycle, some compression. That's the equivalency. We've gathered data from redline air shows and non-jet air shows. We're comparing those two independently to come up with a further reduction for what you'd expect in aerobatic application of the other airplanes. So this is actually some of our test data here, and you see the grouping, which is actually quite closely grouped together here. These were the initial tests that we did to find out, this is for a main 426 83 rivet, which fails at 219 pounds. That's its strength. So you fail it initially, and then you back off just enough that you can start to get a fatigue life out of the hole. Obviously, the tests further up, they rip apart rather quickly. So you want it as high loaded as possible where you get a measurable, repeatable fatigue life. From that, mathematically, we draw a line down to the left on this curve that says that you only have a 0.1% chance that any future event would occur over this line. So that's just your safety zone. And that's what you use to determine your fatigue life. You can see here that here's the stress level. Those rivets that I was talking about, they're either the front and the back of a main rib or the back two rivets on a D cell. Those are the highly loaded rivets, or the most highly loaded rivets, and they fall in this band. And as you can see, here's our test coupons, which are running at about 150,000 limit cycles. And these tests out here, if you equated the life there, it would be between 1 million and 10 million limit cycles. So that would be like an RB-12 lasting over 1 million hours at that. But we have to also consider the aerobatic loads, which has a significant reduction. This is a different way to look at the same graph. So that was log scale on the last. You can see the numbers go 10,000, 100,000, a million, 10 million. Most of us are used to looking at a linear graph. So this is a linear scale. You can see how quickly it falls off. So as you drop the stress by half, the life increases significantly. So the future tests that I've already alluded to that we're currently conducting, and there will be more tests. Again, we've sat down with our third-party consultants and asked what could the worst case scenarios be, make a list, take the top 3, test those, and then come back to the problem after we learn and determine what tests we're going to do next. What tests are valid and will get us the best information most quickly. Overload the crack at various orientations. So as I explained, we're moving the failure point around the crack, its orientation, and other variables are being varied as well. The rib flanges, test coupon that you can see on the upper right there. So testing notches and the rib flange itself, where we can vary the shear force and the pull force. The full wing residual strength demonstration. So we're just going to demonstrate the strength of the wing, which is really showing compliance to that car. There's also a later FAR that we're aware of as well. In comparing ourselves, that's a Part 25 requirement. We're using it as guidance. Crack detectability is a function of size and location. So if a crack would grow, how fast is it going to grow? And from what we've known so far, that is, if it ever did grow, it would grow very slowly and be detectable. We don't want to just say that. We want to prove that. So that's further testing that's going to go on there. Moving on to quick build fuselages. For those that have had them and built into flying airplanes, all load carrying stringers are not laser cut. So the main members that are carrying the load are never laser cut, and most laser cuts parts are very low stress. There's only a handful of parts that we've identified these possibilities, and we haven't gotten a full analysis of the fuselage structures yet. RV 789, 10 QBs have very few laser cut parts. It's mainly the 14 that had the capacity for laser cut parts in the fuselage. But again, if you think of like a tail cone structure, the ribs in a tail cone would be much like the ribs in a wing, where the loading is fairly low. Ribs are for the most part low stress. They're in a wing. We might have some concern with the inward most rib because it closes off the box. We're looking at loads of that right now, the last couple of days. And we might recommend replacement of select parts, but we're not going to do so until we get done with our analysis. Advanced will be testing full wing assemblies. As for quick builds, if you have a quick build on order, is what this slide is addressing. Giving the timeline, what it really takes to get a quick build through the system. And it's 2 to 6 months for us to even get the parts in the container. It's 40 to 60 days on the water. Shipping is improving, but it's still not perfect yet. It takes 40 to 110 days at a quick build facility. Return is 40 to 60 days. And inspection and crating time, running through inspection and getting into a crate and getting you aligned with the carrier and getting out the door is another 30 days. So you're 7 to 12 months by the time that we have new parts that are produced and leave here and go back. That's probably the best case scenario would be 7, and that's pushing it. So what we're offering up is, if you don't want to wait that long, you can convert to a standard kit. We understand, but overall, we're just encouraging you to wait for the test reports. So we don't know exactly how long it will take, and that as you learn something that may lead to further tests, and we just don't know that yet, but we have probably at least a month and a half that I can see easily of testing ongoing forward. We don't want to just test and be done with testing. We want to test properly. And this is not a case where we can take any shortcuts. So we would need to follow down all of these paths and be assured that our answer is correct. Standard kit lead times, there is a minimum run size efficiency. So it isn't that we can just produce one or a few parts at a time. It takes a lot of setup time, especially at the press brakes. So there are minimum run sizes, and the way we produce parts is we have to produce all the kits one by one, and that takes about 6 months to get through that process. I've shortened down, reduced the size of each of these sub-runs so that we can get through them more quickly, and I've also inserted laser makeup runs into that production process so we can get parts out there for you that are building currently. We also must continue to supply our quick build pipeline. There's people working there, and we just can't shut things off completely for an indefinite period of time. So we have parts produced there to introduce back into the quick build pipeline. And then we have long-time lead finish kits that many of you know about. We're finally making progress on improving the rate at which we can fulfill finish kits. But those orders have been on the books for a long time, so we still have a responsibility to fill those orders. The service information that we'll release, in essence, if you look at that list that we have online, I've already identified the spars as red, that we recommend that you replace the spar. The reason being, even though it's very unlikely that a crack will progress, if it did, that's across a member that was across a critical failure, and we would not want that to happen. So we're requesting you replace those. But until we have the full analysis, I would hate you to go in and replace the spar, and then we tell you later on, well, you should have replaced the part right behind it. So just have patience, and thank you everyone for the patience you've had thus far. We'll get through this and have a full analysis for a subcomponent. When we have that, we'll let you know. And at that point, we'll let you know the parts within assembly that we recommend replacement of. For flying aircraft, from what our testing is showing, that it's unlikely that anything would happen. So there's no need to ground the fleet for those that have laser cut parts in it. currently, as we feel from our testing. Would be sometime, if ever, if anything did happen. And again, we're possibly identifying further parts once we know our load analysis. And then on that list that has a risk classification, just know that that will be moving up and down. We'll let people know there's already an email that went out for those laser cut parts, so we'll be continually communicating as we update that list as we get certain assemblies. And then just moving on, we'll have time for questions at the end. And again, a very good way to answer these questions either after this forum or come by the booth if you have specific questions, we can answer those there. In 2021, it took us a year to get this. This is a new punch press that we just put online. We had another new one a couple of years ago. But the difference with this one is it is a foot wider and 2 feet longer. So when you think of what airplanes you can produce larger airplanes. When you flatten out the flat pattern, you can, it has a width to it. So if you wonder why your tail cone is so high and why your rudder has a cord that it does, because it can fit on a punch press, not only the aesthetics and the design of it aerodynamically. So there's a lot of factors. This will open up the world though and be helpful for the 15 and other airplanes. Production welding. We have a welding vendor that was making some of the inch counts for the finished kits that are critical. We bounced back and forth with them between 10 and 14 parts, which are behind. And they've increased from 30 to 45 mounts a month. We've also increased our welding staff in-house. It's a slow process. This is a quality weld that we're doing here on these parts, aircraft welding. We just can't take the welder off the street. And that's starting to come to fruition. Finished kits are going out the door at a higher rate. Production, our composites facility, which we've used since 1989, they're in a small town. They didn't have a lot of labor available to them. And now they're finally ramping up as well. And these are cabin tops that are waiting to go out with kits, but they're able to increase their production rates as well. This is a new gantry router new to us, but what this will allow us to do is cut our own tooling and then larger parts that sometimes get bogged down on our only DF10 that CNC's large parts. So this will open up the world for making composite tooling, especially for the 15. RV10 seats. So during COVID, there was a 6-month period, I remember, when we had 8 seats from our vendor. And we knew we had to do something. Price also doubled. And of course, we sell you a kit price X. And when it gets delivered after it's went to 2X, we need X price. So in this case, we designed our own seat. Here's a test of that seat. So the concept, this is a seat that sits on top of the wing spar, and it is a crash-worthy seat. So that the patent that was on the previous seat is that there can be no flexure at the bottom of that seat. And then the foam compresses on top of the seat. What's meant to happen is the foam slows you down to a stop and you don't rebound. So either the seat bottom or the foam doesn't let you rebound. It's the rebound that hurts your spine. And we had to make a very stiff, rigid seat bottom, much as you'd see in the conventional world. And that's the lead weight that's hanging off there. And that's 43 more pounds. That's 4,000 pounds. That's 43 more pounds than a 2022 Model 3 Tesla, which is not lightweight. It's, as you know, they have batteries in them. So that's what we're hanging off there, is that test. You can imagine the Model 3 right there. And that's assuring ourselves that the seat bottom doesn't have flexure in it. New wingtips come by the booth. We do have our new wingtips starting to come out. Our vendor there, you can see the wattage and the specifications. I won't get too much into that here. One of the innovative features of this is it has a convenience light, so if you've ever tried to tie down your airplane in the middle of the night, there's a light in the back that shines under the wing in the tie-down area. So it's a product that we feel will pull us into the next era of vans and have a quality wingtip, especially if you look at production airplanes. We have a new flat motor. We came off the first flat motor, it was rather slow. We replaced that with a more high speed, and we backed that into the other airplanes. It's available for all the current models. It has integrated flap position, and we've also increased the flap deployment speed on the RV-10 from 87 knots to 106 knots, and that's a requirement of certifying the RV-10 in Brazil under Mosaic. The interesting thing we found, though, and I always kind of inherently knew this flying the RV-10, but the lowest stall speed is actually not at full flap deflection. Now, full flap deflection is still there, so you can use the drag and come in at a steep descent rate. For those of you that have RV-10s, just know that your highest coefficient of lift is around 21 to 25 degrees. Mosaic and expanded LSA. You've all heard about it. I'm not sure how many people have read all 318 pages. I am chairman of the F-37 committee that writes the means of compliance, the standards at which we are going to design Mosaic aircraft. You'll notice here one of the largest factors that affects vans is Brazil, and next month we'll be rolling airplanes off the line. In Brazil, VSO equals 61 knots. That's with the flaps down, 30 speed, and the FAA proposed 54 knots, VS1 flaps up. Currently that takes the 10 and the 14 out of contention and possibly the 7, but we're working on that behind closed doors. That's one of my major efforts here at the show this week. The other things that are exciting, if you own a flight school, we're working on an IFR standard that would allow SLSA aircraft to conduct IFR operations. And as you know, the news media is covering this better than I can at this point, so I'll leave the other details. But what I'd like to encourage everybody to do, we need to comment on this NPRM, but don't comment right away. We'll have a message from vans, the EAA plants a message, and what we need to do is not say various things or our opinions, but have a unified message to the FAA, is this is how we want to improve this NPRM. This is our one chance. Once you have a rule in place at FAA, Mosaic is different in that it didn't have a congressional mandate, which is highly unusual. We actually lobbied the DOT, of course we had a NAC lobbying, putting pressure on the FAA, and that moved us forward. But the only way to change this is to go through Congress in the future, and that takes years. So I don't want to just stand by and accept what we have here. We need to make the changes that we want in this rule, but we can, before it gets locked in stone. So again, wait for messaging from vans. And this is our, in an act in Brazil, Mosaic is already approved. Again, with the stall speed of 61 knots, and that's their assembly line there. And as you're familiar with our drop test methods, that's full RV-10 being drop tested. That airplane is now compliant to ASTM standards, and those are the ASTM standards for Mosaic, which are more aggressive than the previous light sport standards. And in production, and we should see the first airplanes, I hope, get their airworthiness certificates this next month in August. In the United Kingdom, we're getting types to countries around the world, so we can sell the airplane into flight schools outside the United States. We'll report here on engines. Everybody knows the high cost of light-moving engines, as well as engines in general, so it's not just light-moving. I like to note that a Rotax 916 costs more than an IL 390, just to give context once you put all the accoutrements on the edge of it. But we're looking for ways to help light-moving curtail those costs. This is a new throttle body from Airflow Performance. It's slightly larger than the throttle body that's in existence now, and as a result, a slight increase in manifold pressure. The speed gain is not much, but it is going to increase performance. This is what we is flying on light-moving engines moving forward. This is a project that's going on in Brazil. For those that are outside the United States, diesel is a concern. Running jet fuel due to the price of fuel. I was just in Europe at Aero, was talking to Rotax, etc. Visit there, and it's amazing what those of you from Europe, you know how high the price of fuel is. So outside the United States, these projects have merit, and this is a 4-cylinder diesel, performance specs there. So flyer who does our quick build kits in Brazil, who's running this project. If you're interested, talk to Claudia at Flyer. They're on the internet, and Claudia will be here at the show as well. This is Robin Koss, put a diesel project from Continental on an RV9. Again, the specs, it's a bit heavy, but he's now moving on to a diesel on an RV14. So for overseas sales, I think that has some merit. Definitely, it's going to be a good installation. And Robin does a great job. We work closely with Robin as well as Flyer. Many of you have seen, I've actually flown this airplane. Our interest from Van's side, this is really Phil's project. Lockwood Aviation and Vans goes back to the early 2000s. We're closely knit companies together. They fly our RV-12s in their flight school. We loaned them an airframe. This is Phil's project, so I won't speak to how he implemented the engine design. Van's interest was to gain knowledge about the 915 and the 916. And the airplane does have very good performance, cruise performance at altitude. Vaporlock and LSA, I'm giving a presentation on Vaporlock at 2:30 this afternoon, so you can come and get further information on that. I won't cover it much here. But there's a service letter for Vaporlock SL78. Please read it if you run low gas at all. And then we're actively looking at how we can improve the RV-12, and we're writing the STM standards related to that as well. New parts of propeller, you can see this is a replacement for the two-blade metal fixed pitch that has ran for years at Van's aircraft. We've had two versions of the metal and now the composite. I can tell you this slings you out of the gate very quickly. It's a fun takeoff, and for those of you who enjoy that, its weight is only 37.9 pounds. In the future, that's going to be an advantage. Right now, just make sure you check your weight balance and how you load the airplane, because that could reduce your baggage weight. With that, I'd like to move on to the RV-15. And I'll take the first couple of slides here. I laid out this airplane, but it's really these gentlemen who do all the work and make it happen, and detailed design to make it special. So again, Brian Hickman here works in engineering. Axel, he's a design engineer, and Axel engineer as well as test pilot. And we really appreciate having him on board. So this is the engineering prototype, and I'd just like to say, with the prototype, yes, we were changing things, but we weren't afraid to try things. One of the goals I had with the airplane, I knew that the airplane of this size would have a tendency for ground loop, so I wanted to shorten up the tail nose as much as possible. And I put the landing gear further forward so you can still get on the brakes without it coming up on its nose, because of course if you have a lot of mass in the back, it's not going to want to come up as much. And then if we look at just shortening up the tail cone so that mass doesn't have as much inertia. We learned a lot of things from the first design, and Axel will get into that. But we're really implementing that in the computer, and Brian will get into the changes. So we weren't afraid to test a number of things on this model to get the aerodynamics right, and that's why you're seeing completely new design moving forward. There's been some discussion. We didn't know whether we would have the space for 4 seats, and really by 4 seats we meant 2 people and kids. And we had shown that view before. There really isn't headroom for 4 seats. But I show this chart here, and this is actually from early on mosaic discussions with the FAA. We calculated the airplanes that are in the market. As you can see, there's a line that runs through here. And when you make a 4-place airplane, you really need a 6-cylinder engine and 260 horsepower. A Cessna 172, it goes 120 knots, and it's not really a 4-person airplane. What I didn't want to do was create an airplane that had a requirement for a 6-cylinder engine, because I knew the price of engines would go up. I wanted to be in the 4-cylinder market, or towards something from 180 to 220. And I feel that an airplane in this category needs the performance to carry 4 people. You have to have 260 horsepower. And you have a smaller engine. I just wasn't comfortable in loading 4 full-size people. There might be some people that find a way to put a 3rd person sitting backwards in this airplane. But really, we're talking about a 2+2 Those two are kids. The real mission for this airplane is a lot of baggage. So 2 people plus everything you want to carry behind you. If you look at the real world, how people are using these airplanes, most it's usually 2 people and a lot of baggage. And with that, I'd like to turn it over to Brian and take it from there.
Since OSH 22, for starters, we've had to expand the envelope of the airplane significantly. Just making it to OSH, I get some hand waves. There we go. The compressed timeline to get this airplane, and it is the engineering test airplane, so whole goal being get to evaluating cabin volume and aerodynamics for the airplane. It was a very compressed schedule with lots of course engineering that we knew would be safe and overbuilt and get the airplane to the point where we can do real world evaluation on what can only really be tested in the real world. And so from there, we got the airplane to Oshkosh with a constrained envelope for what we expected the airplane to be capable of, and speeds and weights and crosswinds, and every parameter you can think of, we had dialed back. Leaving Oshkosh, we were able to broaden that scope significantly, work our way through more aggressive flying, start pushing the airplane on its takeoff and landing distances, and really putting that 220 horsepower to use. Start working out more detailed defined, I guess we'll say parameters that are VX climbs or VY climbs. We got good numbers, but we had to continue to iterate to really get detailed numbers so we can get performance and come back and help that, use that to inform the design. Beyond that, evaluating the new concepts, specifically the landing gear system, we had to really put it through its paces in unimproved rougher fields and purposely get some big drops into it to build upon our testing that happened in the shop at a smaller scale. So I had mentioned handling. So the RV field being such a high design goal of this airplane as we're trying to slot it into the market. Airplanes in this category has, they kind of cut corners on handling or didn't spend as much development effort into really dialing in the control response that we all feel and experience in our other models. And it's very difficult on an airplane this large, with this much inertia, and just this much wing. But as the wing expands, it gets so much more difficult to move this airplane through the air, just from a perspective of the weight versus the location of it. To do that, specifically in roll, we dialed in our hinge position relative to the airfoil, and we did subtle airfoil changes. And then in use of the airplane, we ended up having to go further and adjust the internal bearing of the airplane, which is essentially how far the move sticks in relation to how far the aileron moves, and the proportion of those come in together.
Let me try to translate what you just said, engineering to pilot. It feels good. At the beginning, it was the forces were a little bit heavy. We moved the hinge back. Now it feels good.
Be sure it can distill many months of work. Many iterations. Well, I am a pilot, and I do have to fly chase against him and keep him honest and make sure he stays on task. But
So what you're seeing here is an everyday thing that we work really close together. So this is back and forth every day, all day long. So there's more of that if you see it in the booth. But some of the stuff that he's referring to previously, when we got the airplane here, we
we didn't have some capabilities that we have now. What you see here is a red-looking R2D2 thing. I can't explain it, but it's a load cell. So when I would come back, the discussions around the table were, well, how is it? Heavy, is it light? And the answer was like, it feels heavy. So we decided to figure out how to say, heavy is this. So this is a load cell. So now we were able to work with advanced flight test, and we were able to pipe the data out of this instrument right into the instrument data stream. So we know exactly at what point and what test point we're doing the forces. So now I can come back and say, during the stall before, we were at 10 pounds of pitch before, so the roll was at 5 pounds. Now I can go back and repeat the test point and say, the force came down, the force went up, and now it's this. So very high-tech stuff that we figure out how to do ourselves. And we're also using autopilot to tell us where the location of the flight controls are and where the trim is. So we have a full picture of everything that's going on. At the beginning, I would say it feels light, and Brian would say, well, what does that mean? I said around 3.5 pounds, and at some point I went and grabbed a fish scale, I pulled on it, closed my eyes, and I said, yep, it's about that. He looked at it and it was 3.4. So it's close enough, but this data doesn't lie. So
If it was close enough, we would have trusted you.
0.1 pounds per error.
In other words, we can form our own opinions now. We don't have axles on our. So, it truly has been a game changer being able to log and record data against all the aircraft's parameters. We use it constantly with most every change. Pitch. So pitch control is a combination of, in general, it's our stapulator, the size of it, how trimmable it is, and the response of our anti-servo tabs. So this stapulator is hinged at the quarter chord position, which is about neutral. And what we mean by that is all of the force that comes back through the stick is artificial in a way. It is produced out of this anti-servo tab. There are significant benefits to that. We can tune it to exactly how we want it to fly. It reduces trim drag and whatever cruising position you may be at power-wise or loading-wise. And it is a more powerful structure given a unit weight. So we can get away with a smaller tail that helps us have the power to counteract these large flaps that are on this airplane and the broad CG envelope that's on this airplane range. This is the third horizontal tail to go on it, and there's kind of some half steps as we got there, increasing the authority, changing the structural design, trying to pull weight out of it, pull cost out of the design. The removable, replaceable leading edge is significantly different in this iteration of it. So very, very inexpensive, easy to replace single parts when you do bang it up and dent it. And again, we had to revise control stick deflections. The sliding seat having different people in it, we had to reduce some stick travel and then mess with the response of these anti-servo tabs and how that affects the overall feel of the airplane.
And so what he's saying is it feels good. So original flight test when we got the airplane here, it was very, very light forces in pitch, very light. And you saw the gurney flaps up the trailing end, and you asked those questions, what's going on here, right? And we talked about potentially moving the hinge back to change that. So we've done a couple of things. We redesigned the way that whole tail interfaces in flight now, right? So we tied the trim tab and the anti-servo tab together. Before they were separate, so in some cases you would see them close to each other. Now they work with each other, so they're anti-servo and they're also trim. The area on the trim tabs were extended by bay to 10 inches on the stab. Why is that? So Brian talked about bringing the airplane here in a reduced envelope. So we needed to get the aircraft here safely within that flight test space. So we only flight tested to flaps 2, which is about 25 degrees flaps. And that area was significant enough or good enough to be able to overcome flaps 25. Now we went to the flaps 4. We wanted to make it a little bit more stable, and now we have the forces, the stability, and a really nice, clean, and actually lighter.
And to cap that off, we're a lot closer to a production version of this horizontal tail, but we're not there yet. This may be a 90% solution, and especially how the linkaging system works is going to be updated. Yaw control, much the same. We had very light control forces, and we were able to continue to iterate on the structure to lighten it up. And we started very conservative with our design and how the control surface is balanced, and worked our way back to a less and less balanced tail.
So the forces here were extremely light at the beginning, and I just, by me resting my foot on the pedal, the aircraft kept flying, not coordinated. So we cut the counterbalance in half. There was still too much power steering, I guess, and then we just completely reduced the rudder to no counterarm down. And we're being told faster money, so let's go run.
The thrust line is a big one. As we expanded the envelope, and we have so much power available, and B, we're working in such a wide range of configurations of the airplane, specifically the flaps and the CG envelope. We weren't happy with the pitch power response. So we all know that as we adjust power, we have to trim the airplane, and there are ways to iterate on that design to reduce that effect, especially with very large horsepower changes. And primarily, the way we do it, update that is tweak the actual thrust line of the airplane, both in yaw and pitch. So this airplane started matching an RB-14, and being such a different airplane, we had to continue to work our way to the more production solution. And we're quite happy with it now at a down thrust angle of a little more than 2 degrees.
So the thrust line change here we're referring to is it's just when you go around, when you apply power changes that are massive, this allows you to not have to retrim so much. That's just what that means in pilot speed. The picture you see there is me saying, oh my gosh, we just got this cowling, how am I going to fix it? And if you build an airplane, you've done that canopy cut, and you've done those big things, and it's like, oh my gosh, that's what's going on there. All right.
Yeah. We're going to work through these quicker so that we can get to the videos towards the end. So we still have a lot of work to do, a lot with the wing and the aerodynamics and the flaps and the deployment forces in the flaps. This wing will still be aerodynamically very comparative to the next airplane, and all of these iterations and useful lessons will be learned in parallel with the next airplane's design. Which brings us to the next airplane. So very much still an RB-15, but with the wing is moving back with the tail. So the wing move is allowing for more flexible loading. It is going to allow us to be more tolerant to different power plant weight combinations, being lightweight engines and lightweight propellers, heavyweight engines and heavyweight propellers. So a good iteration, a good lesson learned on the engineering prototype. It worked fairly well with our heavy engine and light prop, and we needed to open that up to support lightweight light wings, stroke 320s, whatever we can do to get a lightweight 180 horsepower up to these heavyweight angle valve motors. So it has a fairly significant change to the look of the airplane. All of the transparencies are changing, the windows, the door is being updated, the A-pillar, the first pillar just forward of the door of the cabin is sweeping back, and the brake of the windscreen is sweeping back, and there are structural efficiencies gained with this. The forward spar and rear spar attached better align with the A and B pillar, and allows to pull some weight out of the cabin. Just a fuselage from a general sense, because we are happy with how the airplane's flying aerodynamically, we're going to move the tail back with the wing to not change that variable. And because the CG follows the wing, we're going to move the landing gear back. And we have other cabin changes to add structural efficiency and weight savings. The wing's getting significant structural refinement right now. It's still in the computer and we're designing. We are pulling the fuel from the fuselage up to the wing. We'd always planned to. And that fuel capacity will get 60 gallons. As we are moving into a production type design, a lot more options are being opened up for custom tooling and extrusions and whatnot to make it a better airplane, better performance. We've learned a lot in the cabin. We've had to revise some controls and ergonomics, and we may move the flat panel to the floor. We're still in development on that, and we'll continue to work on that with the test airplane. There's many other refinements, but sticking with the theme of more options when you're building these things in rate production. So there will be landing gear changes to make it more manufacturable and scale, make it more efficient, and take the lessons learned from this airplane and tune them out into a higher performance landing gear system. And we can move to videos.
Okay, so we're just going to do a couple of quick videos. I know we got to get to questions, so I'm going to go through them really quickly. But this is a takeoff at Aurora, where we live, and what we want to show here is, once Ron gets it, what we want to show here is a takeoff, and it's a full power takeoff. We're going to go into VX, so you'll see the airplane changing angles because we're still trying to figure out what a VX is, right? So you'll see angles changing from airspeeds from 60 to 65. Put the power in. I want you to see, I wasn't trying to track, but as well, but look at the wheel and the white line. Very easy to control. I just put the power in, look down the runway, and took off, right? So that takeoff, so now we're looking at an angle here. The takeoff was approximately just a little bit over 200 feet. And this climb rate, we were at 90% gross. And this climb rate varied depending on the VX from 1,800 to 2,200 feet per minute. Nice. And the angle that you saw there, I looked down at the MFD and I saw, I think, 22, 23 degrees in that climb. So here's a landing. Just want to point out, can you pause for a second? So just want to point out here that these landings, takeoff, there's nothing magical that I'm doing here. This is a normal takeoff, a normal landing. This is not hanging on the prop. This is not like Control-Alt-Delete, you're pulling everything out, right? This is just a normal thing. Very easy, very repeatable to do. So here, I'm just kind of bleeding the airspeed over the runway, and then I'm targeting the line, and then here's max braking. We'll get through that again. So again, look at the stability on the tail, look at the stability on the airframe, just kind of milk it, there's the line, barely made it past the line, and then brakes. So there you go. So that is approximately 140 feet. It's a little bit less than that, but let's just say 140 feet. Okay, next one. The brakes work. All right, this video you've seen before. Let's go to the botch landing. Let's switch over to the botch landing. You've seen this video before, but Ryan wanted to make sure that I showed a bad landing. So here's a bad landing. So I did not realize that there was rising terrain here. It's backed it pretty good, and then I just held the control back, hold it. There's no power change. There's nothing. Just the folks that have transition to the airplane. All I say is, if you mess up the landing, don't worry about it, don't add power, don't do anything, just hold it back and let the land gear do its thing, let the airplane just handle it. And that's exactly what you see there. Alright, being kicked off the stage, so Greg.
Okay, so that's a lot of information, a lot of variety of information. We're really excited about the airplane. Obviously, we have a whole lot going on. We have the four flight gentlemen that are about to come up and do their presentation, graciously giving us a 5-minute overrun here so that we can take a few questions. If somebody has a question, we're going to stick around and we're going to be heading back over this way. I'd be glad to talk to you behind the forum on the other side here for a little while if people want to. But if anybody has a question, I'd like to come up, I'd like you to ask it into the microphone up here for me so that everybody can hear it.
Both are solid rivets.
For the RV-15.
For the RV-15s, pull rivets, but you will have the option of solid if you'd like to do so.
Does the dimpling process matter? Which tool you use, what pressures?
No.
You got a very extensive testing program. One of the first things that you mentioned was that your supplier provided different processes with each order. What are you doing to account for that in your testing?
We can't account for it, and there's no way to know what part you receive necessarily. So we have to assume, we know who received laser cut parts, so then we have to assume that you could have got the worst case scenario. We're not trying to, what we're trying to do here is determine that that worst case is not going to be a problem. If it is, we're replacing that part.
Okay, when are we going to see those torque screws?
The torque screws. We have torque screws in spec. It's a highly debated thing in Japan's aircraft. I use torque screws in my airplane, others do not.
Mine has torque screws.
Right. The prototype shop does not like torque screws. So it's you know, it's a try-gear, tail dragger, slider, tip-up question.
So we've seen a comment in the statement from laser parts that the ones that will be marked replaced, you guys will replace. But what about those of us that completed our full elevators and we need to replace the front and rear spars, the rear spars, glued to the foam and the ribs? I mean,
we're still making a determination on what parts need to be replaced. So we just ask you
but
to.
if we need, I'm not going to be able to just remove a spar in that case. So will Vince, have you made a decision?
We'll
if you're
come
going
out
to
with
a full kit?
We'll come out with a statement on that. Yeah, we know the concern.
We do understand the situation. We have to scope it out. There's a manufacturing question around that, so we need to write all of those answers, and then we will communicate that with you. So
But we're a builder as well. I'm a builder. I understand your concern. I can say that at this time. Fully aware of it.
So for all of the builders that have these effective laser cut parts tuned in all of our components, myself, and I'm assuming everybody here is more than willing to give you guys the time to do your due diligence, as I'm sure, like the rest of you, I am also doing. But I'm just kind of curious, what kind of time frame can we look at?
So I was trying to touch on that with the usual production schedule, which takes 6 months to get through all the kits. I'm shortening that up as much as I can, and using the most economic run size to reduce the run size so we can get through all the kits as quickly as possible, and then in between inserting laser makeup runs so we can produce the extra parts necessary to supply parts to you as builders. The testing time frame, I'm not going to put a time limit on it because if I'm estimating a month and a half at least, but if we find something that requires more testing, we have to do more testing. There's just no choice there. Right. A couple of months, I hope. The way, and we're needing to leave here, but I'll answer this one. And then we can go behind you, deference to the work life. But we're working through assembly by assembly. So